Hey everybody, Dr. A here, and in this video we're going to be exploring another example of sketching shear and moment diagrams using the graphical method. So let's go ahead and get started. In the given information, we're being told to use the graphical method to sketch the shear and moment diagrams. Now, in the figure we're given, here we have a cantilever beam. And if you remember, a cantilever beam is one that is fixed on one side and it's free on the other side. It's just sticking straight out from a wall. Now, on this cantilever beam, which is 15 feet long, we have a uniformly distributed load of 0.3 KLF, that's kips per linear foot. And then at the free end, we have an applied couple moment. We have an applied moment here of 10 kip feet, okay? So how do we go about sketching these shear and moment diagrams? Well, the first thing you always do is what? Well, the first thing you always do when you're graphing, when you're sketching shear moment diagrams using the graphical method is you solve for the external reactions, always, okay? So if I sketch a free body diagram of this cantilever beam, we know I have a Y, a X, and it's a fixed connection at A, so I have an MA here, all right? And then, of course, we have the applied loads. So we have that uniform load of 0.3 KLF, and we have the applied couple moment 10 kip feet here. And we know that the whole length of this beam, let's draw that a little bit better. The whole length of this beam is 15 feet, all right? So by observation, clearly AX is 0 because we have nothing applied in the X direction. Now I need AY and I need MA. So we're going to do this pretty quickly. Hopefully this will be a nice review of solving for externals for you. If I say sum of the forces in the Y direction equals 0, I can say AY minus 0.3 KLF times 15 feet equals 0. And so my AY ends up being 4.5 kips reacting upwards, all right? Now, what about the moment reaction? Do not forget that. We have the moment reaction here. We're going to say sum of the moments about A equals 0. Counterclockwise is positive. And I'm going to be able to say MA minus 0.3 KLF times 15 feet times 7.5 feet minus 10 kip feet. All of that equals 0. And so my reaction moment MA is going to be 43.75 kip feet. And it came out positive, so it is reacting in a counterclockwise fashion there, all right? So there's my externals. Now I've got to get ready to start sketching my shear and moment diagrams, okay? Now, in this video, I'm going to go a little bit faster when I'm sketching my shear and moment diagrams. I'm not going to show as much of the intermediate calculations to get the shear and moment diagrams because in my previous videos, we did a lot of that. We spent a lot of time showing how we get those intermediate calcs. This time, we're just going to go a little bit faster, all right? So here's the shear force in kips, all right? And I'm going to move left to right, just like I always do, left to right. So the first thing I'm going to encounter for my shear diagram is AY, all right? So what is AY going to do? Well, it's going to push me up by 4.5 kips, okay? Now, what do I encounter next that is causing a shearing or slicing effect through the beam? Well, that's going to be the 0.3 KLF, okay? So this is a uniform load, right? And it's pointing down, which means that the change in shear from X equals 0 to 15 feet, the change in shear is going to be this area, all right? So that's going to be negative 0.3 KLF times 15 feet. So what is that going to give us? Well, that change in shear, in fact, is going to be negative 4.5 kips, okay? Kind of writing it off small to the right side there. Negative 4.5 kips, which means that the shear at x equals 15 feet, the shear force should end up closing to 0, okay? And that's because I'm at positive 4.5 and I'm subtracting this area, which is another 4.5, so that closes me to 0. Now, how are these 2 points related? Well, this should be a linear relationship, okay? So I'm going to shade that in. I'm going to make a note here. This is linear decreasing, okay? Why is it linear decreasing? One more time, it's because we have a constant load diagram here that's pointing down. Its antiderivative is going to give us a linear decreasing sense. So linear decreasing shear diagram, all right? What about the moment diagram? Well, we're going to go ahead and stack the axes for the moment diagram beneath the shear diagram in an organized fashion. M is in kip feet. There's X in feet. And again, I'm going to systematically move left to right here, okay? Move left to right. And remember that the values of the moment diagram come from the area beneath the shear diagram. Now, the first thing you have to be careful about, this is what's different about this example. We have a reaction moment, MA, that we have to account for, okay? So I'm going to say, over here, I'm going to say, we're going to say at x equals 0, the change in moment is going to be that reaction moment, MA, all right? Now, that reaction moment we figured out earlier was 43.75 going counterclockwise, okay? So if you remember from some background information, that is going to give us a jump downwards in the moment diagram. So we're going to say this is negative 43.75 kip feet, okay? This negative indicates that it's a jump downwards. So remember, anytime you have, when you're moving left to right, whenever you have a counterclockwise applied moment, or reaction moment, acting on the beam segment, that will cause an abrupt jump downwards in your moment diagram. Counterclockwise, abrupt jump downwards in the moment diagram. So that's negative 43.75. Next, we're going to engage this area here. So we're going to say from x equals 0 to 15 feet, the change in moment is the area of that shear diagram. So that's just 1/2 4.5 kips times 15 feet. And that change in moment will give us what? Let's punch that through in our calculator. 1/2 times 4.5 times 15. That gives us a positive 33.75 kip feet. Positive because this is a positive area. It's in quadrant 1. And so what is that going to take us to? Well, we're at negative 43.75. That's going to push us back up to what? To negative 10, okay? So why is that? Why is this negative 10? Well, remember, we were down by 43.75. We add to it positive 33.75, which puts us at a negative 10 value. How are these 2 points connected? Well, this is going to be quadratic concave down, okay? Quadratic concave down. Now, you might be thinking, well, this doesn't close. Well, it does, because we have to remember that we had an applied 10 kip foot moment at the free end, and this applied 10 kip foot moment was going clockwise. What does a clockwise couple moment do to a moment diagram? It causes it to jump upwards, okay? So this jump upwards right here comes from, back to 0, by the way, back to 0, comes from that applied clockwise 10 kip foot moment. And remember, a clockwise couple moment causes an abrupt jump up in the moment diagram. So you have that abrupt jump up happening here, and this is your moment diagram, all right? And what is the shape of this again? This is quadratic concave down. It's a concave down relationship. Okay, so again, I showed some calculations here, but not as many and not in as much detail as my other videos, because I want to show you guys and all the viewers watching how you can start, going quicker through these calculations. And once you get comfortable with it, you don't necessarily have to show every single step along the way. All right, so hopefully you found this video helpful. If you did, please hit like and subscribe.